Hello and welcome everyone to episode 6 of the HTTP in C server series thing. Today we're going to work on multi-threading because I did a vote on the Discord server and there's only a few of you guys there, but the people who are there did say with a majority vote that HTTP multi-threading sounds the most interesting. So that's what we're going to work on today. Also, really quick, make sure you're subscribed. And also, I have a Patreon in case you didn't know. It's in the description below. It's where I just have donations for my other open source projects and stuff like that, other communities I run. But it's also for that. And also started a Ko-fi where I get 100% of the money that gets donated, which is also very nice. And you can just download monthly or one time. So if you want to support me, but only one time, then just you can send me a few bucks on Ko-fi if you want, if you like what I do. But there's absolutely no other reason to do it. There's no rewards. There's nothing. You just if you like what I do, you can give me some money, and if you don't, then that's fine too. And yeah, thank you. And let's get into it. So 1 minute intro. Horrible. Let's close all these. So if we go to the GitHub, right? Last time we worked on send file, right? And that's neat. And there's one more thing I want to do to finish that up, and then we're going to get into multi-threading. So the thing I want to finish up is specifically, right now we don't serve files properly from the www website thing. And I don't know if I already wrote this off camera or not. I want to say I did, but I might not have. I'm not entirely sure. No, it looks like I only created a file. So let's say I have this cat picture, right? And in the index.html, which by the way, let's run the code. There we go. That's the URL. Paste that in there. Well, I can't hit it today. There we go. So this is our website. But now if I insert an image, which has the source cutecat.jpg. Oh, wow. Cutecat.jpg. Sure, let's do that. Then what will happen is that it just says cutecat. And if I remove the alt tag, it just doesn't load anything, right? And let's put this into a paragraph. Wow. Zed really doesn't like HTTP. That's one thing I noticed. Like, in case you're wondering, this editor is Zed, and it's like, oh, it's terrible. But yeah, look, so the image doesn't load even though it's right here. And the way that, in case you didn't know, the way that this works is that the browser downloads the HTML file, and it figures out, let's look at the response here, gets a raw HTML file, right? This is what it gets. And so what it does is it parses it into the document object model representation, right? Which is inside the browser, it's inside the browser's memory. And essentially it finds an image tag. And an image tag is interesting because that has another request that you should do to get the image, right? So in this case, it's like, oh wait, I'm supposed to grab cutecat.jpg. And there's a few things that it does in terms of caching and whatnot, but generally it will basically go, whoops, I need to get that. And then it'll just try to get cutecat.jpg. And as you can see, this returns a 404. And that's not what we want, right? And the reason it's like this is because we implemented almost everything last time. We forgot to implement this, right? So if we are looking at the root, which is this, where there's like just a slash at the end or nothing at the end, we get the index.html, right? And that's what you usually want. But in all other cases, we say 404, which is not quite correct, right? So what we actually want to do, and I'm going to turn off the AI for this because this is actually, yeah, we have subtle mode now. It's so wonderful. So I can just do like, and then let's see if it works. I wonder if that doesn't work. It doesn't matter. Let's turn on eager mode again. And this is a new feature in Zed. I don't know. Don't know how it works. Don't care. So instead of this, we actually just want to do a HTTP serve file, which is this one. But instead of serving index.html, we want to serve the route. So that's recline.ura or URI, right? And that's already a string view, so we don't have to cast it or whatever we were doing now. And that's not going to work quite yet, I think, is it? Do we concatenate in here? No, we do, yeah. So this should already work. So let's restart the server, rebuild it and restart it. And now the cat image is loaded. And this is because, in case you are confused for some reason that why this works, is as I said, the browser will request cutecat.jpg. Right here, it'll do a request to /cutecat.jpg, which will fall through this statement and then go in here. In which case we go into the HTTP serve file. Let's say the file name is going to be /cutecat.jpg. We concatenate these together, and then we check if it exists. If it exists, we send it, and otherwise we send a 404. Right? So if I go for funny.txt, for example, which doesn't exist, it's going to say error 404. But if I create a file called funny.txt and I write hello in here, now I reload it, and now there's my funny.txt. So that's wonderful. And of course, we don't have to recompile because none of this is hard-coded, right? And you can make an argument for why you might want to hard-code it and stuff like that. And I know that there is a vulnerability right here where you can potentially do this, not in a browser, but in other programs. However, we're not going to deal with that this time. We're going to deal with that next time because that was the second most voted thing that we should work on. But basically, it now works. But there's a quirk. And the quirk is that right now, if I reload the page, what we do is we get back a HTTP, well, it says it's HTTP1, which it is, but we are not quite doing a good job. Because every time, and I can show this, if we get rid of the request logging, where's the request logging? Request, yeah, let's just comment this out really quick. You'll see something. So we're going to load the page once, and look at that, we get 2 connections, once, twice, okay? And the interesting part about this is we're going to just, we're going to do request line. Oh, we don't have request line here yet. So we're going to put right here, we're going to log what the request is. So request line method. So s, and I think these are like this, right? Method len, request line, method data, and then of course request line uri.len and request line uri.data. And I somehow moved very far there, but it's good now. And of course these should be int. And I swear we're going to get into multithreading very soon. It's just we need to do a few things to sort of figure out why we even need multithreading, why we can't just add multithreading for the fuck of it, right? So we see that we get a GET request for the read page, and then we get a GET request for the cutecat.jpg page. And in fact, if I add, let's say I add 10 more or a few more things, right? And they're all going to be things that don't exist, like these different images. Then we see that we get 1 connection per request. And there is a reason this is slow, okay? You would think maybe it's not slow, right? Maybe it's fast, because it looks fast. Like the response times here are on the order of milliseconds, I'm sure. It doesn't say for some reason, but you would think this is pretty quick. But making a new connection for each request means that we make a whole TCP connection. And even worse, if this is behind a TLS, so like SSL or something, so HTTPS, right? We have to do an entire TLS or SSL handshake, which actually takes quite a bit of time to do because you have a few round trips in total, right? And round trips meaning like, from me to the server back to me. And the thing is, if we have a ping to the server of like 100 milliseconds, then to the server back, to the server back, to the server back, right? We quickly reach like a half second times, and that is where it gets noticeable for the user, right? So what HTTP 1.1 came up with, I don't know the RC number for HTTP 1.1. Gotta be honest, it's 2616. Wonderful. So here we have the keep alive. And let's see if maybe it might be RFC 1945 that does that. It does not. Strange. But basically there's a connection header, right? But it doesn't show. So connection. So in HTTP 1.1, there's a connection header. Sorry for fumbling so hard. I'm still trying to get into. I'm really trying to rush through this to get into the part where we write code, but I also want to be sort of explaining things. The connection header is interesting because it basically says, hey, the browser can say, hey, by the way, keep this connection open. And we can actually see that in the request here. If we look at the request, we see that it asks, hey, can you please keep this connection open because there might be more requests. And essentially what keep alive does is just say like, keep the connection open because next time I request something, I can just reuse the existing TCP connection, which skips the entire overhead of making a new connection and doing TLS or SSL handshake stuff and doing all this crap, right? We just skip over that because we have a connection already open. Because TCP is not single shot. Like you can do quite a lot over TCP, right? There's really no need to have the connection kill itself. However, you can say connection close, and that will do what we're currently doing. So we do need to actually parse the header, technically speaking. But for now, let's just, well, yeah, we could probably do that. Let's see. Connection token. So HTTP 1.0 persistent connections. I'm not sure what that is. Is that a thing? Oh yeah, there's some other shit here. Yeah, this is very interesting. But I'm sure this is some sort of extension that I don't care about. But here, there it is. I was looking for this one. Right, this is what I wanted. Because this has connection keep alive, doesn't it? Yeah, this is interesting. This is very interesting. And wow, okay. Well, I didn't know that there's this much to it. Honestly, I thought you just give it the header. And that's what we're gonna build. Fascinating though, very interesting. Okay, so the first thing we need to do is we need to parse the headers, right? But let's skip that for now and dive straight into how we do multi-threading, because otherwise I'm going to lose every single viewer. And so multi-threading is interesting. Multi-threading, for example, C++ has the standard thread primitive. Rust has the standard thread primitive. And this is wonderful because Rust threads and C++ threads abstract away the platform-specific ways that you do threads. But if you do WinAPI threads, for example, on Windows, if you have to interact with the Win32 API, which is in proc thread or something, I don't remember. But basically, you're using specific Windows-specific data types You're expected to call Windows-specific functions that don't work on any other platform, right? These are NT-kernel calls. You can't do this on any other platform, that mainstream platform anyways, right? And then on Linux, you have pthread, right? Which is POSIX threads. And so, these all exist, and proper modern programming languages will abstract this away. I mean, there's like VLang threads, like every single language pretty much has threads. Like I could keep going, right? They all have threads. And but C doesn't, right? C doesn't, because C is a special little child, and C wants to be extremely cool and not have anything and not ship with anything to make you feel really cool once you start a thread, right? And so that's what we're going to do today. We're going to start a thread and we're going to feel really, really cool. And really, the reason we need multi-threading, by the way, is because if we keep each connection alive, that means that we have an entire sort of a read loop, right? A loop in which we just go, I'm waiting for another connection, right? And we eventually terminate that connection, right? But or we don't, right? But usually we terminate that connection eventually. But for a long period of time, our entire loop of receiving and sending data will be occupied by one client. At least in C, right? In other implementations, you might be able to sort of, multiplex it, but we're not going to get into that. So we're just going to open a thread per client for now. And that way, a thread of execution sort of exists per client, and so all the clients can be talked to concurrently. And we're going to start with one thread per client, and we're going to move on to building a thread pool with POSIX threads, POSIX mutexes, and POSIX whatever the fuck they're called, condition variables, right? Thank you. And there's various things that we're going to do, but we're going to start with very simple p threads and one per connection. So here we have this little loop here, and we have handle client, and handle client is essentially a function that will run, do one request, and then it will return, it will break, right? And remember, we have this loop, but we actually immediately close the socket and break out of the loop. So the loop is essentially non-existent in our version right now, because the loop only runs once. So, not a loop. But what we can do is we can actually move the close out of the loop and keep the break in here, or keep the break, get rid of the break, basically, right? And make these into breaks. Break. And also we want to start having a result. So in result 0, and we're going to say result is -1, break. And again, result is -1 and break. So instead of returning, we're going to break. Because, this is now a real server. We can't just hope that the connection doesn't matter and stuff like that. We have to actually do it properly, because listen, right, before we were just closing the socket sometimes, but not on error cases and all sorts of stuff, all sorts of resource leaks and memory issues and whatnot. I'm gonna get into those at some point, but they're not really important right now. So right now, we no longer exit out of the function without first going through this statement. So we have a single return now. Instead of returning 0, we return result. And that should already make it so that we now don't see a new connection per request. All right, so we're gonna do another one of these, and oh, interesting. No, it did close the connection. Oh, that's probably because we said we were not gonna keep the connection open. I presume that's why. Or HTTP serve file closes the socket. It does not close the socket. Okay, then presumably it's because we're actually generating, we're not generating enough headers. So let's generate the connection keep alive header and see if that works. Just because I wonder if maybe the browser is closing the connections. Let's see. No, it's still requesting a new thing per connection. Oh, it's because, yeah, I know why. It's because we need to now respond with HTTP 1.1. Otherwise, I don't think it's gonna try to do that properly. Let's try that. No, that's not it either. Waiting for connections, got a connection. Oh, of course, that's my mistake. It's because we have errors. That's fine, that's fine. So let's actually copy this cat. We have 2, 3, 4, 5, and 6, I think is what we had. And let's close these again. So now let's rerun the server. Sorry, that was my mistake. I felt like, why are we exiting? Of course, if we have an error, we just break out, right? So, cringe. All right, and here we go. So now we see that we get all the requests at once. And looks like we didn't request number 5. Strange. Let's disable the cache. Fascinating. Oh, the second it does favicon.ico, it actually does kill itself. Right. But you see the point, right? You see that, and actually a 404 shouldn't mean that we break out either, because a 404 is actually perfectly acceptable. But for now, let's pretend that that's not the case, and let's make a favicon.ico. Maybe we'll just copy it and name it favicon.jpg. I just don't want any of the requests to fail right now because it's a little bit, we don't want to deal with that. Set the favicon here. Thank you. DuckDuckGo AI, I don't know. It's a wild world we live in. That's favicon.jpg. Wonderful. So now we should also have a favicon. And that seems to work fine. Okay, so now we see that we have a bunch of requests. And I guess it's not really loading the favicon.jpg properly, but it doesn't really matter at this point, right? We see that every time we refresh the page, it keeps reusing that connection, and the connection does not die, and we don't get a new connection. So it's already working. But now we get to the issue, right? The gist of it is now when we do or I guess it's still working. Because it's the same browser, right? Okay. But if I open a different browser, let's say a private window, and so this will load infinitely, right? Because there's actually no way for the second instance of the browser, so that second client, to get any data, because we only have one thread, and that one thread is hogged by the, like, this client can keep reloading, right? And the second this client exits out, let's see if that works. The second this client exits out, we should be able to get a new connection in. Maybe not, maybe we don't exit correctly, but you get the gist, right? The idea is there's actually no way for us to handle more than one client right now. And I love the little picture of the cat up in the icon. That's pretty funny. But essentially, now we get to the point of okay, now we understand the problem finally. How do we make pthreads? So pthreads are actually not that difficult. If you have ever worked with threads in another language, this will be very, very familiar to you. And I think there's like 4 functions we have to call to make this work. Let's see. Yeah, this doesn't really tell me much. Let's see, pthread, exit, pthread join, pthread create. Let's have an example, please. Wonderful, example source code. Horrible, but still example source code. So let's copy this out into an editor. Start another instance of Z. And let's C code. Wonderful. So the way that it says that it works is that you first do a pthread init somewhere. Where is it? Maybe it's this one. Then you do a pthread create. then you do a pthread join. And so it's pretty much the same as any other sort of threading implementation, right? And that's because they all are built on top of stuff like this, right? So let's try doing that. Let's try creating a thread. Well, first of course, we need to change the makefile to actually include here. We need to link with pthread. And on POSIX platforms, you do that with -pthread. And if you're on Windows, this is the part where if you haven't already, you need to switch to Linux or another Unix. I mean, macOS or Linux or any BSD all should implement pthreads, in case you're following along, because there's really no reason why you should be on a Windows platform to do this. Windows is for gaming, not for HTTP servers. Hope nobody's offended by that. Wonderful. So pthread, and then we of course also need to include pthread, which is, I think, just pthread. Yeah, that sounds good. And so we need to create a new thread. Pthread init. Isn't there like attr? I guess there is no pthread init. I guess we don't need to init pthread. That's pretty nifty, because I didn't want to do that anyways. And we can even set like the stack size and all sorts of fun stuff. Or can I just ignore that right now? And let's see. So when we get a new connection, we want to actually run pthread create. And we need to give that a, okay, so this is the output of the thread, right? So this is the actual thread that we're creating. Pthread t thread, or client thread, whatever we want to call it, right? So we actually give that thread. Then this is the pthread attributes, which I think we can probably just null out. We don't care. This is the start routine, and then it has an argument. And so these are interesting, right? So this is the routine, and this is the argument. And these are essentially these, right? So the routine's gonna be handle client, and the argument's gonna be client socket. And there's a return code, but we're gonna learn very quickly that that doesn't matter anymore. And of course, pthread create can fail. It will return non-zero. Okay, wonderful. So RC is, if RC is not 0, then pair pthread create, and we'll move on. And so this doesn't work right now because they're actually not the right signature. So handle client can now no longer return an int. Instead, it has to return a void pointer. And it can also no longer take an int. It has to take a void pointer. And so what we can do now is we can say int client socket is int client socket pointer, because we can just pretend that this is a valid, a valid pointer, right? A valid socket, because, even though it's probably not, it's, this is big enough to fit an int in this case. So we're just going to live with that for now. Wonderful. And so instead of returning result, we return void pointer result. And this is a little dirty, and as you can tell, our compiler is not very happy with it. And, we can fix that later, but right now we don't care. And so client socket is going to be void pointer client socket. And so now this actually compiles again. Let's see. Wonderful, it compiles. Now, of course, not happy, and I get to that. But now when we do this, we can actually do a bunch of requests and then open a new private window and do more requests. And there's absolutely no problem with that. Now, granted, there's one little problem, right? And that one little problem is called, whoops, we didn't clean up behind ourselves at all. And so now if I search for the server executable, we can see that it's using 11 threads. And so if I just hold down F5 here, it'll create a bunch. Let's go back here and also hold down F5 here. Oh, well, it created a few more. So essentially, we now have a bunch of threads, and these threads are not going away, right? They're not going away. Like if I do like, if I request something funny, you see that some threads are going away because they are now killed because there has been an error, right? But the second I come back, it might go back up again, right? So let's, whoops. Yeah, see, it kills a few threads here, but we have an unimaginable lot of threads after some time, so it's not correct. And just for reference, when we start, we have one, right? So we need to actually clean up these threads again. So we do that with pthread join. However, we don't actually want to join it right here because then we have the same issue that we just have one thread. We create it, we join it, which waits for it, and so on and so forth, right? So that's not quite correct. Instead, what we want to do is we want to save all these p threads in an array. Okay, so pthread t threads and size t threads count. And what we're just going to do is we're going to just do a really dirty move here and just say threads is calloc size of pthread, and we're going to have whoops, wrong way around. We're going to have like, I don't know, let's allocate like 10 of them. Or sorry, threads count. Well, actually, we're starting one each time. Let's do a capacity as well. So threads capacity is going to be like 10, count's going to be 0, this is going to be null. For starters, right? We'll get there. And so now we do, we calloc the threads capacity, right? Which, by the way, calloc's just malloc, but it zeroes it, and it has a nicer syntax for this. Right? And so now every time we do this, we push the threads in there. So we say threads at threads count plus plus, or let's do it explicitly. Let's be nice here. So again, we need pthreads t thread we increment threads count, and then right here, if threads count plus 1 is bigger than threads capacity, which means we wouldn't have space for the next thread, we actually just pthreads t pointer new threads. We realloc, and realloc basically does the same thing as calloc, but it actually moves memory around when there is no more memory to basically grow, right? And this is basically the implementation of a vector or like any sort of dynamic array. And I'm sort of just shitting this out. I'm not really doing a good job here because I feel like we're going to touch this code a lot more, and I don't want to do too much over engineering right now. There's this saying, how does it go? Complex software that works has always grown from simple software that works, but or something like that, right? But simple software that works cannot be achieved by reducing the complexity of like complex software or something. I butchered that so hard, but basically the idea is build it simple first, then increase the complexity, and then it's going to be fine. Other way around doesn't work. Well, I butchered that. I'm so sorry. So we grow the capacity by 1.5 by reallocating the threads capacity times the size of pthread t. If new threads, if not new threads, we actually pr realloc, and we go to exits or something like that, right? can go to exit. And otherwise we actually reassign threads to new threads. And the reason we do this little dance where we create a new one and then assign it later is because in case it fails, we don't want to lose track of where this pointer is, right? Because we want to keep this pointer so we can free it later. It's a pedantic thing. Nobody really gives a shit, right? If you exit the program, all the memory is reclaimed, all the threads are killed, stuff like that. But the more we work with C, the more we have to sort of be very, very anal about this and be very cautious and make sure that we do everything right, because if we don't do everything right and nice and sweet, it's gonna blow up, right? At some point we're gonna forget to deallocate a resource because we think, oh, surely the OS is gonna do it, and then it doesn't, right? Like a file lock, the OS doesn't know what the fuck a file lock is. It's just gonna not throw that away, and suddenly you have a bug or a problem or some sort of other issue, right? I'm a yapper. Holy shit. Okay, sorry for swearing. Right, so threads is new threads, and at that point we're good. So this is essentially a grow the vector. If there's no space left. Yeah. Right. Yippee. Let's continue. On exit, we'll actually go for size ti equals 0. I less than threads count, not capacity. Important detail. And we're actually gonna go pthread join. Let's see. Can we kill? I think we want to kill the thread. And the reason we want to kill the thread is because our reads are blocking, and I don't think we'll ever actually join. So, yeah. Threads I sig term. We need to include signals. Right, so now we kill all the threads, which seems reasonable. I think we're allowed to do that, right? So archman pthread kill. It's been a minute since I used pthreads, so let's see. I mean, at this point, we don't really care, right? We're just trying to clean up as best as we can. And then, of course, inside of the thread, we want to pthread exit with result. Because this is cleaner, right? So let's do that. And let's see if we're missing anything. Oh yeah, we want to also set a timeout on the read so that I think we want to do that in the future, but I think for right now we might be fine. Let's also print something here. Closing connection. Fuck it, that's fine. That's good enough. Maybe we can print the result. Okay, let's see. Oh, uninitialized? Oh, right. So again, we're running into that issue. Let's allocate these at the very fucking top. There is no reason not to. Wonderful. These are warnings we don't care about. What have we got? Get, go to connection, get, waiting for connections, get, waiting for connections, closing result. Right, okay. So this seems reasonable. And of course, the threads still linger, but now we actually know that if we kill the program for some reason, we will actually kill all the threads too, and it's gonna be clean, clean-ish, right? Good enough for us right now. Let's see. So now we have multi-threading, which is pretty satisfying. The only issue is, right, like these threads were the most simple threads we could make because they don't interact with anything. If you have any interaction because you're trying to write some smart logic, maybe you're trying to write an API or something like that, you can't just access variables from the thread, global variables or other functions or stuff like that. You have to be very, very careful. And there's a lot of functions you're not allowed to use. Right. So, for example, the reason that it works for us, that it's legal for us to do this, is because we wrote our own parser, right? This is our own parsing logic, right? We don't do like this is a proper multi-threadable implementation. If you do if you have static variables, static buffers that you allocate, right? Maybe you do str talk, right? Let me just show you what I mean. Something like that in your program, because you couldn't be bothered to build stuff like this. You do actually have to be very careful because you cannot call those from multiple threads. If you absolutely want to, if you need to, right? So, and I'm talking about this version, right? The version where you just use the static buffer. Right? If you absolutely need to, you can put a mutex around it, right? Let's just say that. But that does make your entire server fuck-ass slow. And it even says here, each call to strtalk modifies a static variable is not thread safe. And not thread safe is not just like, oh, that's not safe-ish, right? That will blow up so bad, right? Don't fuck with it, okay? If you call any functions other than like memcopy, memcompare, string length, like a few basics, right? Be very, very, very careful because threads are disgusting. Threads mean that anything can happen at any time, pretty much, right? And you can't rely on any of your static data or any of the functions that modify static data to behave in any way that is predictable, right? So unless you use mutexes and stuff like that, but we'll get into that when we build a thread pool. But yeah, basically now we have nice nice multi-threading, and because we're so funny, let's see how much our server's performance has improved here. So let's do O3, and let's even FLTO optimizations, and we're gonna make, right, and then we're gonna do server dev null, and we're gonna run siege on it. What's the port? 6969? Wonderful. I'm so funny. And we do actually want to run the parser. And so let's see how fast our implementation is. And so the first thing you'll notice is that if I look only at our server executable here, you see that it's actually balling pretty hard, but it's not as hard as it should, because let's run this in an external, because I think Zed's terminal is struggling with that. Let's do 6 thread or 5 threads maybe. And let's actually filter for server. Whoops. Server, there we go. So you see that there's 1 thread now, right? And now we start the siege. And we see that our server is now jumping between 1 and 8 threads or something like that, But of course, if we say we want, I don't know, 20 threads, then suddenly we jump between 0 and, well, 20 threads, 1 and 20 threads, right? Because we continuously start a thread and then close it and stuff like that for all the different things. And, you know, you have to remember that this does actually load images from disk and things like that. So let's see, and we're at 15,000 transactions per second, which is pretty good. It's not that fast. And you'd think, you know, why? We're literally doing like the coolest thing ever. We're just making a thread per client. Like this should be maximum performance, but it's actually not, because making a new thread takes a while. And you see our throughput here is 6.92 megabytes per second, which is pretty abysmal. But let's commit this and then I'll show you why. Let's commit this. So we don't want to commit that actually. Let's get rid of these because we don't want to commit those. Yes, yes, yes. Yeah. Well, we technically are HTTP 1.1 now, so let's keep that in. And all the other changes, basically, I want to have all of them. I don't want these changes just because I don't really want to commit all of that stuff. And now, so add multi-threading. And if you are, if you have the repository starred, you would now get a notification of some kind that I did just update the repository, even though the video is not uploaded yet. So that's pretty hype. You should start the repository and subscribe, of course. Make sure you subscribe and like the video, of course, right? So now let's go back. Let's go back one commit. And let's actually add FLTO and O3. And let's make wing. And let's make that again. And now let's run the server. I'm piping into dev now so we don't see the output, which because the output's slow. And now let's siege it. Let's see if it's any faster. You'll notice, of course, that, well, you would notice if it fucking worked. You'll notice that we now sit at a comfortable 50% CPU. We have only one thread, right? Because I just went back in Git history to the point where we didn't have threads yet. And now we can see that we have about twice the performance. So adding threads actually didn't make it any better. In fact, it made it 50% worse. And the reason for that is mostly that we have overhead in terms of the amount of, like, creating threads is expensive. And I'm actually going to show you that this is the case, because I think it's really important for people to understand that you can just figure this stuff out with tools. You don't have to guess. And the fact that I'm guessing right now that making threads is the culprit is actually pretty stupid. So if I now do the same optimizations I did before, and I make a clean build, and instead of just running the server, I run it with callgrind, which is callgrind tool callgrind. We can see, we will be able to see what takes so much time. And so now if I run a siege here, actually, let me go back to my terminal. If I run a siege again with, let's say, 10 threads, or maybe I actually want to pipe that into dev now because I don't actually want to see all the output, and output is slow, as I said. Right, so we let the siege run for a little bit, and this is called profiling. Okay, and profiling is really important, and I think we just crashed. Did we crash? Yeah, I guess we did, but it doesn't matter, right? It doesn't matter because, oh no, it does matter. It does matter. Well, we just do that again. I have a macro, an alias for that. But let's just run the siege for like 10 seconds. Let's see if I'm recording still. Wonderful. Okay. Wonderful. And now let's kill the server. And now we can use something like kcachegrind to inspect the callgrind out file. And we're actually going to put that on like monitor 4 or something. And I'm sorry for the flashbang here, but this is kcachegrind. And it actually tells us where we've been spending so much goddamn time. And so if we look at the HTTP serve HTTP handle client function, which is apparently where we spend like 100% of our time, like 86 to 90, like 86% of our time is spent here. We can now look at the source code, which is annoyingly not colored in, and we can see what is taking so goddamn long. Let's see. Let's see. Okay, this all seems pretty fine. Okay, so pthread exit took a long time. That makes sense, right? As we exited. What else took a lot of time? Memset took a lot of time. Ooh, interesting. So for example, we can see here, and I know this is very confusing. Let me actually just pull up the graph. This is easier, or the color map. But this is fine. So we have main, right? Main is right here. And main calls HTTP handle client, right? And handle client, 40% of handle client's time is actually, and let me, can we not view all this fucking random shit we don't care about? Please. Huh, guess I can't. Well, let's make a node cost minimum of like 5 or something, so we have a little bit more space. But basically, let's have a tall layout. You can see that handle client calls HTTP serve file, which is 43% of the entire time or CPU time we spend inside HTTP handle client, right? So 43% of handle client is a HTTP serve file, which makes sense because that's the only function that does shit. And then actually what we can see is that 35% of the CPU time in HTTP serve file is used up by memset, which is pretty abysmal actually. So let me turn the minimum node cost down a little bit. Yep, that's still the case. So which is 80% of HTTP serve files time is spent in this memset or multiple memsets. So let's find those memsets really quick. I think my voice is disappearing, but that's fine. So let's see. There's one memset here where we set the entire buffer to 0 for the file data. And there's also one memset up here where we set the file name buffer to 0. So if we want to optimize this program, and you can see right now we managed 1,400 transactions per second, which is slow as shit, but that's just because we're running inside of callgrind. So your callgrind results will be worse. Right, but essentially what we're going to do is we're going to optimize this a little bit because I don't see why we shouldn't, pretty much, right? So if we look at this, we have this call to memset file name buff. Memset file name buff, and of course we're in regex mode, so that doesn't work. There it is. So this is actually taking a shitload of time, and that makes sense because file name buff is actually 4 kilobytes, and so because it's 4 kilobytes and we're clearing it every time, we're actually doing 4,000, well, up to 4,000 memory writes. It's going to be less, but like 1,000 or so memory writes or 500 memory writes at this very point here. And that's a lot of memory writes to do for just sort of, oh, let's just make sure, right? So let's get rid of some of the safety here and let's see if we can optimize this. So getting rid of safety was a joke, by the way. File name buff. So we mem copy the web root and then the file name data. So at web root len plus file name len will have a 0 byte, right? That's all we care about. So let's do file name buff at web root len plus file name len is 0. right? Because all we want to do is null terminated. Which actually, do we need to do that? Oh yeah, we do need to do that. But essentially now there should be null terminated. So to make sure that's the case, let's actually print it. By first mem setting it to like, this is a thing that I like to do is like setting it to, I don't know, X or something. And then we print it. File name buff. And this, we can just sort of double check our logic here really quick, right? So make server. And now I'm just going to load the page. And we see that there's one X here. So we're actually off by one. Let's see if that's right. Yeah, that looks right. Of course, we should probably put a \n in here. Yeah, looks good. Cruel. Well. And yep, seems to be working fine. Right. So now that we've identified that there was a bug here, we now no longer have a mem set. And because we no longer have a mem set, we now have unutilized memory, but we don't care because we null terminated, so we don't care. And that was the first one. And the second, incredibly horrible, apparently, one was, where was it? Ugh, sorry for the fucking flashbang, as I said. I'm looking at these numbers here. So there's one here, memset buff. Memset buff, size of buff. This is line 21 in fs.h. Oh, right. Okay, so here we're actually reading the entire... What are we doing? Oh, it's the same thing. It's the same thing. We're mem copying some stuff around into the buffer. And I know I could use string copy, but I highly dislike it for my own reasons, so that's not. So let's just not terminate it like that. See if it still works. Oh, I no longer have my cats in here. Let's do that again. 3, 4. God, Z is being annoying. And 6. And of course, we also want the favicon, so meta. How do you do that again? Meta favicon, blah blah. Oh, link rel icon. Fuck off. What? Such a joke language. Okay. Actually, this is an image JPEG. God, what the fuck? I didn't have a J key for a second now. What the heck, man? All right. Okay, so here you go. Wonderful. Now works, still works. And because I changed some stuff, I'm actually not entirely confident that these changes are going to do it, but it doesn't matter. We're going to just run again. So make and let's just make and callgrind. Callgrind the server. Run another siege. And you now see that this page is also bigger, and we will do more requests because we now have all the JPEGs of the cats and stuff like that. VGN segment. Fuck off. I don't know what that means. I don't care. But essentially, we just have to run it for a few seconds. Kill it. We got 2,100 transactions per second, which I would say is faster, but we don't really know because we know our sample size here is abysmal. But let's open it again. So this is the new one. And so now we actually spend 4% of time. Before we spent, no, we spent 37% of time here in HTTP server file. Now we spend 10% of time in HTTP server file. So we've optimized that. So now we have to figure out what is taking so long in handle client. And let's see what is taking so long in handle client. It's kind of hard to see, actually. Interesting. It doesn't really want to jump to the function here. It's quite annoying. So kcachegrind is cool, but it's not like the perfect tool, right? You can tell it's a little funny. Oh, no, caller is what I want. No, callies is what I want. So this calls pthread exit, which takes a lot of time, right? Because every time we exit, we actually pthread exit, which takes quite a bit. So maybe we actually want to avoid pthread exit and just return. Do we need to pthread exit? I don't know this actually. Let's figure that out. Okay, do I need to pthread exit? Yeah, I understand this. That's not my question. Let's ask the AI. See if it knows. Probably does. Oh, I can just return. Okay, wonderful. Because returning is going to take much less resources than calling pthread exit. So let's really go back to this. I think I'm making this video abysmally long. Yep, I am. I'm so sorry. Okay, let's try that again. Let's again call callgrind on it. Run it for a few seconds. And I mean, throughput hasn't improved, of course, right? Because we haven't actually improved anything. We just made it so that it takes less time now, right? The overall thing. So let's see, compare. Oh, right. So now that we've gotten rid of this sort of false positive of pthread exit taking so much time, because it doesn't really impact our HTTP server's speed, because it's at the end of the routine, and we spawn n threads, so we don't give a fuck. But you can see that it was sort of poisoning the data set because it was taking so much time that all the other stuff sort of fell over off the table, right? So now when we go back, we see, oh, actually split string is now taking most of the time, which actually makes quite a bit of sense because it does a lot of weird shit, like mem comparing, right? And because we're mem comparing and we're doing if statements that seem to fail a lot, I think, yeah. So a lot of the times, so every single time actually, because there was nothing to split at, I guess, it just skipped over this routine. And so these are inefficiencies that we could get rid of. And this is where we get into sort of really optimizing this. And I don't think we should optimize this because, you know, there is not a big use to it right now. But we can now see that this sort of string splitting routine is quite slow. And memcompare here is actually quite slow, which is interesting. I didn't think it would be. But I guess we're comparing at each I we compare with split by. Which, by the way, this is only used for CRLF comparisons. And at some point there is no performance you can squeeze out, right? Like just because there's a big number here doesn't mean that this is bad. It just means that you're spending a lot of time here. If this is sort of the core of your hot of your hot path of your code, which in our case it is, right? Like parsing the request is quite literally the only job that the HTTP server has. The fact that this takes quite some time is actually reasonable. It means that we don't have anything unexpected, right? This is part of parsing, and we do send a lot of headers, so we do a lot of parsing. So, reasonably, it's probably quite slow there. That said, 2000 transactions a second inside callgrind actually means that outside callgrind we should be pretty solid. Yeah, outside of callgrind we have 16K, which is still slower than the last one. Of course, just because we have the overhead of calling the pthread create every time. And I bet you if we, let's see, pthread create, yeah, pthread create alone takes 6% of our time. And that's not counting that potentially there might be time here that's not even counted because it's spent in the kernel. So, I mean, there's a lot of printf, right? All this printf is just us logging stuff. And when standard out is not a TTY, we could probably turn all that off, for example, right? So we could get 18, 20% improvement in speed just from removing log statements. So there's a lot of stuff we could improve here. Anyways, I think that's it for today. I think that was interesting, and I think we did a little bit of making it better but making it worse type shit. So lots to do still. Thank you very much for watching, and if you're still here, leave a little comment and join the Discord and tell me that you actually watched to the end, because it's very interesting to me to know if people actually watch this long. Thank you very much for watching. I appreciate you. I appreciate your time, and I genuinely really, really appreciate all the support I got. It's absolutely mental how much support I got on those videos. The first video in this series got like 1.6 thousand not likes, that'd be interesting, views, which is a lot for me. I've been making YouTube content since 2012 maybe, and all my old videos are unlisted, so you won't find them, but I've tried everything, right? And I'm glad that something's finally working out. Thank you guys for watching, and I will see you in the next one. Bye bye.